Hey, John, can you hear me? Or Jamerson, can you hear? Give me some feedback. All right, gotcha. Thank you. All right, 1 more minute. Yeah. Well, that's the last piece, and then we're gonna do the failure sequence simulation with the hydrothermal stress in there. Yeah, hydrothermal, and then we do that's the final thing. Yeah. All right, so 3:50 now. Let's get started. Sorry, I have you push off today. I actually there's a Boeing proposal call for researching the composite material. I responded, so I was invited to send a second round. It was sent to Boeing. Hopefully, I don't know. We'll learn this Friday whether. So that took me all day, right? 2-page write up for composite research. Okay, so we have you all had completed maybe 80-90% of the code, which is CLT calculation. You want to continue to add in the hydrothermal functionality, and then we're gonna have a final project user code to do a failure sequence simulation that basically tie together the failure criteria we learned to simulate a sequence of failure from first ply failure, second ply failure to final failure. You're gonna reproduce the loading sequence that leads to final failure. That will be the final thing. So as far as the lecture is concerned, I'm gonna start covering some special topics, which is a sort of a more or less standalone topics, things of interest, especially for aerospace composite structure. So today I'm gonna try to touch upon two things, buckling and fatigue, composite material. All right. So the main source of this lecture came from these 3 books. You can find them and try to read more if you're interested in more information. Those are the very good source. All right, buckling is a phenomena that is a sort of a instability phenomena. We learned that in solids. We learned a buckling of column when column under pressure. There's an Euler equation you can predict. If you recall that actually buckling has to do only with the stiffness. It does not have anything to do with the yield strength. Okay. So same thing happened to plates. When you load a plate, the plate can buckle. You push the plate from one direction, it could buckle. When it buckles, it kind of develops this sort of outer plane curve. Part may bulge out, part may bulge in. And it can buckle under compression from one direction or compression both directions, or tension one direction, compression one direction. You have to have compression. If you tension both directions, I guess membrane buckles, but plates usually not buckle. If you put a plate, composite plates or shell as a part of a pressure vessel, you put high pressure on it, the plate will be in a biaxial tension. They don't buckle. They rupture. They don't buckle in that sense. You put a composite plate under a shear load, it buckles. Shear and compression are the required load to produce buckling. When it buckles, it has excessive outer plane deformation. Part bulge out, part bulge in. Sometimes it forms certain patterns like waves. Like the wave you see here in the composite plate. You see these part went in, part went out. They form this periodic structure. So there is a mode of buckling. So that speak of that has to do with the mode. Some of the mode is we talk about first mode, second mode, third mode, just like a vibration mode. There's a buckling modes. Like the plate under compression, it could develop any number of different modes. They have different threshold load. It could have a one dip, one protrusion, or 2 protrusion, 1 dip. We're talking about the different half waves. Okay, that's a buckling phenomenon. And buckling are vulnerable of aerospace composite because people tend to make it very thin. People tend to make it light and thin. They're sometimes millimeter thin, big structure, very thin. With of course stringers, with reinforced stringer, they buckle. It's one of the limiting loading case. Okay. So when a beam buckles, it's very dangerous. You're close to failure. When the beam start buckle, its structure about to collapse. So like a building, a column supported building. When a column start buckle, it's about to fail. It's like downhill. It go down and never, probably not come back again. When a plate buckle, you see this load displacement response at the knee. There's like a knee behavior when you load the structure. In this case, it's a plate under compression. All sides are simply supported. You see suddenly a knee happen. Basically, your stiffness changes. Your structure becomes softened a little bit. It bends. You keep loading. It actually keep carrying load. You want to deform more, you need to put more load. So there's a positive slope after the first mode buckling occurs, and it keep going up. You can still carry load. So when the plate buckle, it doesn't mean it fails immediately. It means it has structure has changed response, but it can still carry certain load. So we speak of that knee and what happened before. We use a term called the post buckling behavior. The material has a post buckling strength, can still carry load. Okay. The second figure basically speak of the effect of initial imperfections. When you have a plate which is a perfect geometry, very straight, no imperfection, then you have a sharp knee. When you load to the threshold load, it bends sharply. If the plate has some initial imperfection, like it was bowed a little bit initially, then you don't see the sharp change. You see this gradual changes depending on how much imperfection you have. If the material already bowed a little bit, when you push it, it bows a little more. You keep building that direction. Sometimes you don't even see the knee. You see a gradual transition. Okay, that's a difference between the plate behavior and a regular beam or column behavior. All right. The buckling is like a bending problem. It's not an eigenvalue problem. Involves a fourth order differential equation. The mathematical theory about it is given here. So the governing equation for the plate bending, this is actually highly simplified cases. We're talking about a cross-ply laminate. The ABD matrix is greatly simplified. You don't have any coupling terms. In this case, the cross-ply symmetric, all the coupling terms are 0. In this case, the governing equation is simplified to the fourth order differential equation shown here. And we have the boundary condition, which is basically means all the 4 edges are simply supported. There's no moment, the displacement 0. In that case, there exists sort of closed form solutions. There are very few cases in terms of buckling and post buckling. There is a closed form solutions. Most cases you have to use numerical tools to solve them, finite element code, things like that. But when you have an analytical solution, what it allows you to do is develop further understanding. The closed form equation give you a lot of insight into the dependencies of things. So for this special case, this is from Bob Jones' book. If you're interested in there are more details on there. They're actually a very simple solution for this problem. The buckling load, this is under uniaxial compression. The buckling load is given in that equation there. So you can see it's very similar to, anybody recall Euler equation for beam buckling, for the column buckling? What is the Euler equation? It is, what is it, pi square EI over L squared, right? When you calculate Euler column under compression. You see that equation give you the threshold critical load for the beam to buckle. It has nothing to do with yield strength. It has everything to do with the modulus, the stiffness. Now, if you look at this thing, it's very similar. It's a pi squared d. What's the d? D is it's like a stiffness. It represents some sort of modulus in a bending part, and some geometric quantity. So m is a buckling mode. M has to do with buckling mode. It's the number of half waves you develop. One half wave m equal to 1, two half wave m equal to 2. And A and B are the size of the plate. You can see for plate buckling, the solution is kind of similar to the Euler equation for columns. Basically, the buckling only depends on how stiff the panel is. It has nothing to do with the strength, the stiffness. Okay. So if you build a material thicker, stiffer with bigger d terms, in this case D22 is the governing term. You increase that term, you will increase the buckling threshold for this plate. Okay. That's the beauty of a closed form solution. That leads you directly to the most important parameters in optimizing or designing this. If your buckling is your limiting case, you pay a lot of attention to these d terms, D22 in this case. Okay. All right. So the solution for this equation is plotted over there. So basically, what's plotted is the buckling load function aspect ratio, A to B ratio. And those m equal to 1 and 2 are different buckling modes. With m equal 1, you have a 1/2 wave. Just 1/2 wave. When m equal to 2, you have 2/2 wave, up and down, 2/2 wave. 3 is the 3/2 waves. Up, down, up, down, 3/2 waves. Now the equation to the right is the approximation when A to B is very big. That nx to the right is the asymptotic value of the buckling load. For very plate with very large A to B ratio go to infinity, you have that solution. When A to B is finite, you use the equation to the left. When A to B into infinity, you use that special terms. All right. Now with this equation, we can look at a very interesting case. This is a sort of a design of a plate. Let's say if you design this plate against buckling, buckling is your mode of failure of interest. So you could you use, let's say you use same amount of material. Okay, same number of plies. You can lay everything in the same direction, make it repeated UD laminate, just bond it up. All the fiber go in the same direction, build up thickness. Or you can use the same amount of material, you alternate, you go cross ply. Now, obviously, in the case to the left, all the fiber along the same direction, you would have the largest compressive stiffness. It is the stiffest of them all, because the cross ply, remember, is controlled by matrix. It doesn't have a lot of if you do this and this, the cross ply doesn't contribute to the stiffness. It turns out that for buckling situation, even your load in that direction, that is not the optimal case. Optimal case is you put some fiber also in the other direction. Even your load is on the fiber direction. For the plate to resist buckling, the most optimal case is when you have a cross ply. You have alternate axial 90, axial 90, 0, 90, 0, 90. That's because all the other terms. D11 is not only one that controls everything. These term matters. So to make the overall term the largest, the cross ply make more sense. They actually give you these terms that overweight this term. Okay. So that is an interesting observation. You need to reinforcing the transverse direction in order to avoid buckling when you load it in the fiber direction. the lens direction. Okay. Now, when you have this is cross ply, 090s. When you have angle ply, symmetric angle ply, you can also calculate all the D's. If you then use a similar equation we presented before to calculate buckling load, you find that it over predicts. So angle ply will have a lower buckling threshold. So the dot in here, the empty dots are the buckling load when you have angle ply, but you instead using the early equations to calculate anyways. It actually give you a little bit over, I guess 50% more than what really is. The experimental value is a solid circle. Okay, so basically compared to cross ply, your angle ply will have a lower buckling threshold, assuming the material is the same. You just lay up difference, same amount of material, same type of material. Okay. So layup have an impact on the buckling threshold. And buckling can occur under shear. So you have a plate, you put a shear force on it. You can solve a set of partial differential equations similar to what I showed before. Assuming again it's a simple, little simpler properties. We don't have a B, we don't have a bending extension coupling, and we don't have a bend twist coupling. Those are required to simplify the governing equation so make it solvable. Under those conditions, also for the range A to B from half to 1, and we have this solution. This is also a closed form solution that predicts the buckling load for this plate under shear load. Okay. You see again, it's very similar to Euler equations. It's pi d. It depends on d. D is the basically stiffness of the plate, bending stiffness of plate. Okay. And depend on dimension, depend on d. Okay. And there are situations where the plates is under both compression and shear. If you look at a piece of plate, on a, let's say, sort of rocky case, if they have a transverse load, you easily create a situation there's both compression and shear. There is a simple equation that you can adopt when you have to analyze a case like that. You can do a break and conquer. You can analyze the same plates under a compression load only. You find its threshold, the critical load, which is NX critical. That's a bending, that's the buckling threshold under that single load. And then you can figure out NXY critical, which is a threshold load under the shear loading. All right, and this curve give you the failure condition when both loads apply at the same time. So if your X load is less than X critical, XY load is less than XY critical, put them together, it could be critical. Even both are under combined cases. When that's equation roughly equal to 1, that combination. So this is more like a failure envelope for the case of a buckling load under combined loading situation. But this allows you to basically analyze more complicated situations. So put this equation for shear and this equation for compression together. You analyze two problems, and you combine them together, and it can give you some guidance for what would happen when two loads are applied together. Okay. This is a very useful model. All right. The boundary conditions have huge impact on the buckling threshold. If you have simply supported, SS is simply support. That means you basically restrict the deflection. You don't restrict the rolling. You just restrict deflection. And clamped is where you restrict both the deflection and the rolling. It doesn't rotate, it doesn't deflect, that's clamped. So the loosest boundary condition is SS all the way around the plate. That will be the least amount of a constraint. In that case, your buckling threshold is lowest. So the least amount of a constraint results in low buckling mode. You give it more freedom, it tends to buckle at lower load. If you clamp all the way around, if you take a plate, clamp all 4 edges, rigidly clamped, then you're in the case all the way to the right. In that case, you have the highest buckling load. Okay. The constraint help reduce buckling. And then you have the mixed situation in the middle. For one case, you have one pair of sides clamped, the other pair of sides is simply supported, and vice versa. They have kind of similar buckling response in the middle of this. So the other way to reduce buckling or combat buckling is to add more constraints at the boundary. So that's basically very basic set of information regarding buckling. On Friday, we'll do some calculations using these equations, using our code to predict giving compare the buckling responses to different plates. We calculate these using our ABD calculator, and then use the equation to predict buckling loads. We'll do that probably online too on Friday. This is I'll upload this online so you have this with you when you calculate. It's a very useful set equation. Give you some first-hand estimation, the magnitude of things. When you have a piece of composite plate at hand, it's always good to have some order of magnitude. You know roughly what order of magnitude it takes to buckle this in certain ways. Okay. All right. The other part I want to talk about is fatigue. Fatigue is a big concern for metals, as you're aware. You learned that thing in junior design, solids. It's almost like a cancer for metals, all metal fatigue. If you keep the load cycles back and forth many times, eventually the fatigue crack will take over and destroy the thing. So there's no cure. The only cure is you reduce the load, or you do preventative maintenance. You actively look for the crack. When it hums, you deal with it. If you turn a blind eye to it, let it cycle, eventually you catch by surprise. Okay. The latest experiment for the Pratt engine you see on the news, I think last year, one of the fan blade fractured. It's a titanium fan blade. It's hollow fan blade, and there the cracks start from inside. The fan blade actually is hollow, using some sort of lost back casting process. The cracks start from inside and propagated over time, and knock the, it goes out and knocks half the blade off, and the engine become unbalanced, and the broken blade also damage other things. The engine went out and started a fire. Luckily, the plane didn't lose control. The other engine was able to take the plane safely back to Denver. That was a pretty lucky event. There's a good chance if you lost an engine on an aircraft, the plunge down. As we know, the helicopter is also known as a flying fatigue machine. Why we call that? Because it vibrates like crazy. If you look, helicopter is the way it operates. The level of vibration, it is just it's a fatigue, walking case of fatigue. So basically, Even you use composite is known to be much more fatigue resistance than metals. They still fatigue. There's still the question, how long will it last? So it is necessary to understand the fatigue behaviors of composites, which is drastically different than metals. Metal usually is dominated. When the metal fatigue progressing, it's usually dominated by single crack. There's somewhere with stress concentration, and then the start of the single crack. That single crack start growing from baby size to bigger and bigger and bigger. It's pretty straightforward. Composites is way more complicated. Composites in homogeneous material. There are not a lot of interfaces inside. There are a lot of different material inside. Those interfaces can produce something called a sort of a distributed damage. Damage grow everywhere. The internal boundaries can separate. Fiber inside can break in a sort of a diffuse fashion over fatigue load, and that gradually accumulates. The composite also strongly anisotropic, especially carbon fiber composites. One direction is very, very strong. You can put a fatigue load, you don't see much difference. If you put fatigue load in the matrix directions, you see the effect pretty short in a short period of time. It cracks very quickly, but you don't lose the function. You still function as a composite. You carry loads. So these things compounded together make the material process of fatigue way more complicated. Not the same order of magnitude. You cannot track a single crack, understand the fatigue of composites. Okay. To give an example here, this is the experiment conducted by a group at Virginia Tech. So it's a notched carbon fiber composites under fatigue loading. The R ratio is 0.1. R ratio is mean was divided by high. When you put a fatigue loading, you can do tension compression, full reverse. That R equal to -1 because your minimum stress is negative, right? Tension is positive, so the ratio is -1. When you have zero stress to high tension, the R ratio is 0. Your minimum stress 0, then they're high stress. And this R equal to 0.1 means that you have a small amount of tension and then go to high amount, and then you repeat. That's R equals 0.1, right? So this is a notch plate under that kind of ratio. You basically applied it. You first measure how strong the material is. The material turns out that the picture to the left is the coupon when you just pull it to break in one cycle. You can calculate its nominal strength is 364 megapascal. That's how strong it is. As fabricated, you just pull to break. And then interestingly, the B part is you first load the sample to 80% of its strength. You put 80% stress and let go. Do R equals 0.1 cycle. You half a million times. You just load it 500,000 times. And then you stop your fatigue loading and you pull the brake. It becomes stronger. The failure stress, the nominal failure stress is 459 megapascal. People call this a wire in. Wire in. They're wire in and wire out. The reason for that to happen is when you fatigue the material, you effectively reduce the stress concentration around the notch. The material around the hole that produce stress concentration, they're increasingly cracked up. So the stress concentration factor actually become less. You create a better situation. But if you keep going, you keep the 80%. You keep the 80% stress. And then you go for 1.3 million cycle, it breaks itself. So that's a wear out process. So this is a complication of fatigue. You don't see this in metals. Metal doesn't show this behavior. They go straight down. They don't become stronger over time. The composites could initially go stronger, 12 million cycles, and then you keep going. Eventually, it becomes weaker and dies. So it's very interesting. And the process, what happened inside the material along the process, is a key to understand why the material do that. Do this kind of behavior. All right, for metals, this is a sort of a schematic for the metal fatigue process. It's a single crack starting from a very small size comparable to the grain size. The grain is a tenth of microns, usually a few microns, tenths of micron. Starting at that scale, you have very small, slip planes that grow into a crack. That crack keep going to a microscopic size. As you cycle them, this is during tension, your crack tip open up, and then you form a maybe a local yield zone or process zone, and then once you compress, that tension compression process leads to the progression of that crack for a small increments. Every cycle you make a little increment. The increment could be very, very small, microns or even smaller. And eventually you propel the crack to a size that reaches this fracture threshold. And so the energy that drive the crack to grow is the mechanical energy input. The cycling energy is you pump the material essentially. So every time you cycle it, there energy loss during the local yielding. So you're loading, unloading, you lose a little bit of energy, as shown in the hysteresis. Those energy is what drive the little crack to go forward a little bit every time. Okay. And then later on, once the material break, you look at the cross section, you see the beach marks. The beach mark are those little increments. You can actually count the beach marks to see how long this has been happened. Okay. And the telltale sign for people to believe that Pratt engine is a fatigue problem is that they look at they fished out the blades. They found the blades, broken blades, and they look at the origin of the fracture. They found the beach mark leading from a corner of the internal cavity out to a bigger crack. So that's metal fatigue. Now, composite fatigue. This is a very nice sort of an illustration of what's going on inside a composite material when you put it under fatigue loading. It's way more complicated, and the damage more diffuse. It occurs everywhere. This came out a special topic book by Ken Riefleiter. He's my advisor, PhD advisor, Virginia Tech. So he basically described this pictorial. This basically shows the damage process the first damage that occurs when you put it under fatigue loading is matrix cracking. You start having more and more matrix cracking. They're more or less independent. They're sort of they usually form with certain spacings. We call it characteristic spacing. They don't usually come too close, because once you have a crack, due to the shear lag phenomena, the material near the crack is unloaded. You cannot put tensile load on the material near the crack anymore. So you will not have a crack right next to it. You had to go a certain distance to build again. So you see this almost regular spacing things occurring in the matrix. That's the characteristic matrix cracking. Now that's the initial stage. There are also a small amount, the little dots are the sparse fiber breaking. Now at the tip of the matrix cracking, there's some stress concentration that results in fiber 0-degree fiber layer will start to have some small amount of fiber breaking events occurring. Now, as you keep going, what happened is the matrix cracking start linking up. They're like attracting each other. They not only go in horizontal direction, they actually turn vertically. That become a delamination. They separate. They go and delaminate. The cracks are coupling, form a zigzag shape. So these are individual cracks, individual crack, and they start talking. There now become a delamination. And that process worsens as you go a little bit more. And you have a bigger delamination that make the two layer large area separates. They don't have mutual constraint anymore. And then you have more fiber breaking. Now, at some point, the fiber breaking become localized. So you have more fiber breaking near the tip of these. There are more fiber breaking and more fiber breaking, more fiber. So this also gradually, so these are greatly weakened layers. These are start to be weakened, and the weakened zone become concentrated near this area. And at some point, one of the weakened zone start sort of coalescing. They form a rounding through crack, and that separate the material. That will be the general process for fiber for carbon fiber composite material. The initial cracking occurs pretty quickly. This basically shows the initial effect. When the initial matrix cracking, you lose your stiffness. You can measure the material become low softened. You can put strain gauge and measure stiffness. You put a load to see how much strain. The initial cracking leads to rapid reduction of strain, and then it come into a dormant period. The things progress slowly. You have quasi flat plateau. That means the property didn't change very much. It's hardly sensible, flat. And then the final stage, it goes very fast, accelerate again. As you have more diffuse damage, they coalesce faster and faster, and the accelerator shoots to the failure points. So this is a good and bad. Good is that you have very stable middle period. You could have very long fatigue life. Even though you have enough matrix crack, you can things last long. But there are no signs for final failure. There's very low signs. The worst case, the downside of it, it's hard to predict, get warnings when you should, reject this part, when you should retire this airplane, retire this wing, change new parts. No warning. Or internally, as against the single crack self-similar growth in metals, internally there's this wheel turning everywhere. So you have local damage events, which is really limited in certain location, micro cracking, delamination, and that alters stress distribution. Your local stress distribution always changing. So there is one common trend is the fiber, the layer, 0-degree layer along the low direction gradually gets more and more stress. All the stress shedding events, the end result is you put more stress into the direction, into the ply with the fiber aligned with the low direction. So this wheels keep turning through the entire process. You have damage, low distribution, damage, low distribution. And this is the early signs of crack. You can observe these directly or using a technique called replica. There's a set of compound you can mold to the side of the plates because the composite structure are huge sometimes. You don't get to carry this into SEM, but you can use a replica. You stick this replica compound, you harden it on the side of the and take it back and then use SEM to look at the replica. It gives you all the features of this. It tell you all this crack, okay? What happened is you start seeing, for this is a 8-layer lamina. What you see is crack occurs in the cross layer, which is 90 degrees, and then the plus minus 45. And they have two different kind of spacing. The 90-degree one is denser. So on the very top is the 0-degree plies. There's 8 ply. You can count the very top 0-degree 0-degree ply, and then below is 90-degree plies. And that's where you have a denser crack. And then you go to the 45, plus minus 45. You still have crack, but the cracks are less dense. You see the spacing? Also due to the angle. 45 goes that direction, so it appears longer. That too. And then you back to the plus minus 45. So there are 4 angle plies in the center, and then back to 0 plies, and back to the fiber 0-degree plies. So that's first stage when you have these occurring. All right, the local delamination is another thing that occurs. So if you have crack running in both directions, let's say you have crack running in mainly in this direction. That's your, this crack is within, this is an X-ray image. These examinations are occurring by, so you fatigue the sample. Then you introduce a penetrant. It's usually a liquid with heavy elements, like iodide, which produce a heavy X-ray shadow. You infiltrate the material with those compounds. And then you look under X-ray and you see the shadow. The shadow is where there's entrapped those element penetrants to give you a shadow. So you see the shadows here. The shadow, when the crack running in the horizontal direction in one of the layers, and another crack running in this layer, when this crack meets this way, and that point is pretty vulnerable to develop a delamination like this. When the two crack is like this, and that stress, if you do local micromechanic stress analysis, the local material near where the two crack cross is very adverse stress state, is under so-called triaxial tension. The local material, if you do finite element analysis, is being pulled in all three directions, which is the worst case for most material. Most material can resist pretty high compression. If you compress the material equally from all sides, you can argue some material never break. They are infinitely strong. If you pull the material, they become weaker usually. If you pull the material from three sides, that's worst case. You can do it to a material. Even ductile material, if you pull from three sides, they can become brittle. Okay. So at those cross point, due to the adverse stress state, the local delamination occurs, which is basically local separations. The layer are not bonded anymore. And then the other thing that occurs, this is a microscopic evidence showing the fiber breaking. So this is one layer, the 90-degree layer. You have matrix cracking like this. There's a crack here, and there's stress concentration right over here, because this usually carries a small amount of tension stress, and now the stress is shed. This is not carrying any stress anymore. The stress actually transferred to this stress, to this layer. This layer carry more load. In this zone, you start having these breaking events. So basically, that picture shows the SEM of a material in between the area and near the area. You see in between the area, very little fiber breaking. In this area, there are more fiber breaking here. These are fiber breaking here. This is a telltale sign of fiber breaking. Is you see the free ends of the fiber. So that's occurring. So the other key idea that Refliner proposed is to sort of divide layers in laminate into two camps. One we call the critical layers. Critical layer is the layer, when that layer breaks, the whole laminate is gone. That usually is a layer at 0 degree to the load direction. If a major load is tension this direction, the fiber at 0 degree aligned with that direction is the critical direction. If the fiber goes, the rest of the thing cannot carry the remaining load. So, and then Refliner also proposed you focus on this layer. When you do analysis of fatigue life prediction, you basically predict the remaining strength of this layer. You treat the other layer as spendable. And you, once that layer is spent, you calculate the stress redistribution and calculate the remaining stress on this layer. And you use this layer as a critical element to do the fatigue analysis. That's the basis of this idea. So basically, the evidence show that the 0 degree layer, the critical layer, undergoes small amount of damage every time there's a little crack hits it, and this accumulates over time. So you're losing little by little its strength. Notch is commonly seen in composite. When people join composite together, frequently people use fasteners, right? You bolt, one section of airplane together with the other section. So you drill holes on them. You had to deal with the holes. When you have holes, you basically open up a can of worms. The hole is stress concentration, and the stress concentration is also dependent on the layups. So this is what happens. The stress concentration attract damage too. When you have a notch sample put under fatigue loading, you have a highly likelihood to have a damage occurring around the hole. What you see here, this is again X-ray image, dye penetrant X-ray image. The dark area are the damage zones, become loose. They're cracked up, delaminated. When you put a dye in there, the dye infiltrate into it. So when you do X-ray image, you have dark shadow because the material are heavily damaged. The damage actually show different patterns depending on layup, but they're heavily populated around the hole. Okay. This is a picture to the left and right shows the different patterns when you have different layups. This one have a 0 degree layup, and this one has no 0 degree, all 45 layups. This is the type of material you would see the wear in and wear out phenomenon, as I showed before. The material initially becomes stronger, and later on become weaker. And the reason it becomes stronger is because all the cracking events occurring near the edge of the hole reduce the effective stress concentration. There's more X-ray images showing the progression of the damage. Damage gets really, really big. It goes, it almost at this stage, initially concentrated on a hole, and at this stage, propagated almost 1/3 of the remaining width. In this case, went over half the remaining. So you grow in both directions. You grow in this direction and that direction. It just become increasingly bigger and bigger. Another layup. The layup affect the direction the damage goes. This is a weird way that damage actually occurs over there, which is kind of interesting. Right underneath the hole, you're pulling this direction. And this close to the end of life, the damage almost occurs throughout the material volume. And the other interesting thing people have observed is the for a notch sample, compression is really a bad thing. You can have fatigue loading, which is R equals 0.1, which is a tension fatigue. Small tension is big tension. And you can have a fatigue of R equal to -1. You have a tension compression fatigue. It's bad because once you delaminate, remember when you have a free edge, when you load the material, there's a interlaminar stress. Whenever there's a free edge, it'll tend to separate them. During tension or compression, the layer tend to separate at the free edge. Then you press them a little more, the separated material becomes single layers, have almost very little buckling resistance. When you push them again, they tend to locally buckle. The local buckling, let's say that you have 40 layers, and then due to interlaminar stress, under fatigue loading, your first layer delaminated. Then when you're under fatigue loading, the delaminator tend to buckle out. That single layer has no buckling resistance at all. The remaining 39 layer does. It bond together. That single layer on the free surface has 0 buckling resistance. So when you press it, it bows out. And that actually separates them a little more. It peels off. And you repeat this more and more times, that layer completely peel off. And that's the picture shown in the one. This is a fatigue of notch sample under reversible stress, fully reversed cycle with compression, tension and compression. And then the layers peeled off to look at the delamination from between first, second layer, second, third layer, all the interfaces. You see the first layer delaminated huge amount. That layer separated around the free surface and buckled. and then that delamination propagate to a bigger area. So compression combined with tension is pretty bad for notch samples. It accelerates delamination. One of the few measurables you can use to track the fatigue progression is you measure the modulus. You basically measure how stiff the material is. If you touch string gauge, you just pull, you put a certain load and you measure the strain. The ratio of stress, nominal stress over strain is the modulus, right? You track this modulus. As the material weakens, the modulus become lower and lower. You plot stress strain curve, basically the curve become less and less, become flatter and flatter. Okay, and you track that throughout the whole fatigue life over many cycles. And this is the general trend for composite. You have initial rapid drop due to matrix cracking in the transverse layers, and you have a long stable region. That's region number 2. And then you have suddenly falls. It's like dropping off a cliff. A few drops, the material is dead. So the long dormant period and then the precipitous ending. Rapid decay, stable, and then rapid decay again. Now people have tried to use a technique called acoustic emission to monitor composite structure. Have you heard about acoustic emission? Acoustic emission is when the fiber break, it gave off a burst of energy. You pull a rubber band, you pull hard, it breaks, the rubber band springs out. It releases a little bit of strain energy. That strain energy sets off a curve, sets off a wave propagated into the material. It's usually in a sort of acoustic range. It's a ultrasonic range, sorry. It's a several hundred kilohertz frequency. You can measure it. If you use a sensor which is sensitive enough, like piezoelectric sensor sticks to the surface, and that sensor pick up this little burst energy, you can actually count how many times it occurs. You can classify this signal and associate some with fiber breaking. And then you can stick that sensor on the material for forever and just record the occurrence of these things over time. And then you can possibly detect the burst events. When you have initial damage, when you go to this region, what happens is that you have more and more. You can accelerate the fiber breaking. Fiber breaking become more and more frequent events. Okay. And that indeed is a technique people apply to some of the civil structures. Not necessarily composite, but similar to composite, like the cable stayed bridges. There are many cables on the bridges. Those cables are actually listened to by these sensors. When that fiber start popping one by one, accelerated fashion, that means the bridge is about to go. So same technique can be applied to composites to as a way to monitoring. The other way, there are many ways to monitor. People have used a wave method, like they're sending a wave through crack samples to measure the attenuation. The crack material has higher attenuation. People have used X-ray, so on and so forth. As far as the data fitting and the prediction is concerned, Rick Schneider at Virginia Tech has proposed a method he called a sort of residual strength method. So he actually proposed a set of formulas that you can first calibrate with a set of Essen curve. You can then apply this formalism to arbitrary laminates. So the key parameter this code tracks is something called a residual strength. So you assign a residual strength for the critical layer in the laminate, and you track its evolution as a function of cycles and its number of cycles. And then the F number is a failure criteria. If you recognize that, that's actually a failure criteria that we learned before. We call it failure function. So you track the failure function of the critical plies, and you can calibrate a set of equations that predict how those equations, how the residual strengths evolve over time, which is the curve on the top, which is the residual strength reduction curve. Given a loading cycle, given an initial material property, you can predict this, how the residual strength decay. This is predictable, but you need to do some experiment to calibrate. And then you can compare that to the EPA load. When the residual strengths drop to a certain level that actually match with the EPA load, that's where the failure occurs. That's one point in your fatigue life. Every cycle, you solve this FR as a function of n, you get this curve, and then you solve the n value when this FR equal to the EPA load, and you get a failure points. And you predict the 1 point in the S-N curve. And you can impose different loads, which results different residual strength reduction curves. So residual strength can reduce slower if you have less load, and that give you a different reduction curve and then a different point in the S-N curve. Long story short, this is a methodology. Early generation of composite Air Force has used, particularly F-16 design. They use this methodology to do the fatigue life prediction. And it's backed by experiments. The experimental predicted value, the curve, and then the measured value are shown here, the observed value and the predicted value. It's quite interesting that it actually match pretty well for this case. So you can see when you apply different load, the residual strength reduction curve can span, can be quite different. Some can be, much flatter than others. It sort of drop much later life. This is a log scale, by the way. This is a log. So this actually, if for linear scales, it's hugely different. There are more technologies to and more formalism to sort of data fit S-N curves to predict fatigue-like composites. This is just one of those. But just the reason I put it out here because I was familiar with this. All right, so that's the brief introduction I have today for you to know. If you, again, there's these resources that if your research involve these subjects, you're highly recommended to go for the sources. Very comprehensive resources are those 3 books. All right, any questions, comments? Anybody here is doing fatigue research? Buckling? NDE? So what type of NDE technique you guys are? Okay. So what kind of damage are your, what's your target damage? Oh, stainless steel, not even composite. Okay, I see. Yeah. All right, that sounds good. Okay, I'll see you guys on probably Monday. I'll do the online thing again on Friday over Zoom. All right, I'll see you guys later. Thank you very much. You too.